Hello, very dear colleagues. My name is Muqaddam. I should thank our dear colleagues for organizing this series of courses. I should thank Dr. Bosch, Dr. Raqib, Project Director of URP, Rajupart, Mr. Hilali, also our dear other colleagues, General Ali Khan, Mr. Shahid Alam, and our very dear colleagues in S8A component of URP Rajupart. I should also thank Mr. Rudra, Mr. Guni, Miss Salam, that managing the sessions for their very good coordinations. Also, thank to our dear colleagues in Engineering Staff College of Bangladesh for hosting the program. I again ask dear Ms. Salam and Mr. Guni that if there was any problem with, especially with audio, as our respected colleagues, some of our respected colleagues mentioned that there was some problem, please tell me. I try to switch. Then at that time I will switch to the cell. As it mentioned, this is the fourth and the last session on existing buildings. We reviewed some concept. We reviewed that for existing buildings, the R factor values in the new building codes are not applicable because when we use those R factor, the assumption is all the detailing and the ductility requirements of the new building code for that specific structural system are done and carefully applied, implemented in design and in construction, which we know for existing buildings, often most of them are absent. Then what we should do for a systematic evaluation of existing building? From a systematic evaluation point of view, a building that consists of different elements, in each element it consists of many force-controlled actions and deformation-controlled actions. So our task in the systematic seismic evaluation of the buildings is checking the demands and capacities for each of these force control and deformation control actions. We talked about a static linear method. In a static linear method, the demand for all of these force controlled and deformation controlled actions are derived based on the calculation of a base shear. So in a static linear method, base shear formula is the starting point calculate demands. In non-linear static method, the demand is calculated by deriving a target displacement formula. So base shear for the static linear and target displacement for non-linear static was our clue to find and estimate the demands. When we, for example, in the linear method, we calculated the base shear and applied to the building and find all the values of force control and deformation control actions. Now that we have the demands, we should look at the capacities. Regarding capacity for force control actions, there is always, both in linear and non-linear approaches, for force control actions, the capacity is always the same, both in linear and non-linear, and that's lower bound strength. So it's very easy. For force control actions, the dangerous one, we always calculate their strength based on those formula that we already know from steel code, concrete code, masonry code. Just the value for the material characteristics, we use the lower, smaller values. So capacity of force control actions are easy to derive, and our problem with that part. So then, regarding the deformation control actions, their capacity in deformation control actions. I think, dears, do you want to say something to me? Because I hear the couple voices. No? Okay, I can't. So I ask your co-host to mute if they don't want to tell us. Then non-linear, for the deformation control actions, in linear approach, we use the expected strength, and then we multiply by M value instead of R value. So there is not one unique R value. For each performance level, I, O, L, A, CP, we use different values. And in nonlinear approaches, their capacity is the deformation capacity that for each performance level is mentioned in the tables. So we went through some of these concepts very quickly. Of course, as our dear colleagues mentioned, it is much better if we can go through examples. That we will talk about that a little later. We also look at the application of pushover for existing building in the previous session, and some of our colleagues sent me notes that in the BMBC article 2.5.12, also the pushover for the new buildings are mentioned and is acceptable for the new buildings too in the BMBC. And in fact, that's a very advanced method that is already included in the BMBC and is the same category as adopted by Eurocode. Because different codes, Turkish code, Japanese code, New Zealand code, they have pushover procedures, but their categories are different. The BMBC and the Eurocode are in the same category. Of course, there are some difficulty to model the mathematical nonlinear model and how to use the acceptance criteria. It encouraged that lab test data being used for the mathematical model. And so there are still some points that in the future versions of the code, little by little, they become more comprehensive to be applied for the even new buildings. So with this summary, if we want to look at the topics for our 2-day session, as the title of the session mentioned, is mainly about the modeling parameters and acceptance criteria because in a way they are the most important items uh, in the systematic evaluation. And the point is that in the new buildings, our approach is binary 0, 1. Either we accept the elements in the building site if all the details are implemented according to design, according to the code, or we ask for the demolition of that member and constructing a new member that satisfies all the requirements. But in systematic evaluation, our approach is different because we are dealing with the existing buildings that almost all of their elements does not satisfy the requirements of the new building code. And it's not logical that we destroy all of them, demolish all of them. So the point is how to implement their deficiencies in the modeling parameters, in the acceptance criteria. And that's the concepts that make these new generations of the systematic evaluation of the existing strong and powerful. We talk a little bit about the parameters that control these two important concepts. Also different approaches to them and how they can be derived from the tables that are included in the codes for the existing buildings. Also, there are a couple very important points. In fact, there are three very important points regarding the differences of our approaches in evaluation of existing buildings compared to the seismic design of the new buildings. And one of them, which I emphasize here, is very important that we use different analytical methods as we will discuss. Look at this systematic existing building code. Performance levels, a chapter on the definition of the hazard levels, a chapter on the different analysis method, linear method, nonlinear method, and then they have some chapters on the different materials. So all the information regarding the different systems that are made from that material, usually they are very nicely summarized in the chapters related to that matter. For example, for the concrete, the same for almost for all materials, we have the scope at the beginning, material properties and condition assessment. Second, general assumptions and requirement third. So these three are general things. And then we go to the systems, which is, for example, here, concrete moment frame is a system. Precast concrete frame is a system. Concrete frames with infills are a system. Concrete structural walls, and precast concrete structural walls, concrete brace frames, and then some elements. Cast in place concrete diaphragms, precast concrete diaphragms, and concrete foundation. So, in general, some general items, then systems, and then elements. Very systematic. Later we will see that all the information for each system or each element is given in 5 sections. So these existing building codes try to be very systematic because, as I mentioned, the approach, we want to be complex. We want to be as complex as possible. So we remove any possibility of overestimation by reducing simplification. And because they become complex, so they should be very organized. So we can find, we know that where we should find the information that we need. Therefore, as a sample, we look at the structure of the concrete section. In the first part, in the scope part, it naturally tell us some general statements about the area that is covered by this section, by this chapter. For example, it cautions us that this chapter is not for the damaged reinforced concrete buildings in the earthquake. So it's for the existing buildings that they are not experienced, or they have very small, but not they don't have lots of damages from earthquake. If we want to evaluate a damaged building, it is the procedure. It should be somehow different. So in scope, emphasize that in what conditions we can use the requirement of this chapter for our existing building. Then there is the second part in each chapter is the material properties and condition assessment, which is really the most important, the most difficult, the most time-consuming part in each retrofitting and evaluation project. Is the finding the material properties and condition assessment of the building to find the configuration of the elements and the materials. That's naturally very consuming, needs lots of permission, lots of arrangements. And the way that in this systematic existing building codes deals with the subnauts. At one hand, the approach should be flexible, should give us options. There shouldn't be only one way. You should go do this many tests, do this many investigation, do this many survey, because sometimes there is not possibility for that. So there should be some options, some flexibility, and then based on the level of the knowledge that you gather in different approaches, and in the modeling and in the acceptance criteria, you will have the effect by a knowledge factor. So it is, tries to give at least a couple options in any based on that. Then the knowledge factor can be less or can be more. So sometimes because we didn't collect enough information, our knowledge about the building is not complete, entity is with the and we don't use the complete capacity of the building, because there is some probability that formation is not complete. What is needed? What is needed is these two rows. We decide that we want to check for which performance level and by which procedure, nonlinear. These are the starting point in the approach, and by the other part of table, we try to rank the level of knowledge that we got for an existing building. So then we put some of decisions that we should make after decisions that we made about the performance level, about the analysis methods. Then we need three parts, different information about the building. So these are the decisions. These are the informations that are needed. Some related to number of testings, some related to the drawings of the building that we should use for modeling, and for the condition assessment, configuration of the elements, dimension of the element, their situation. So this will be the needed information, and then the output will be the final output will be the knowledge factor. What immediate will be the situation of the elements and the properties of the matter. For example, here it says that if you want to check the building for life safety or lower performance level, such as the collapse prevention, you can use the minimum level of data collection, minimum level of data collection. But if you want to check, for example, immediate occupancy, you should use comprehensive data collections. Of course, for life safety, for damage control, you can also use this. So you have many choices. For some situation, your choices are limited. For some situation, you have many choices. And for the testings, sometimes in some of these choices, we don't do any tests. Either we use the default values or the values of the material properties as mentioned in the drawings and documents of the existing building. Sometimes the number of testing increases. Just as a check, do you have my voice? Still, do you have my voice? So every now and then I check. Miss Salam, Mr. Guni, do you have my voice? Yes. Do you have my voice? No. Switch to this. dear, dear Mr. Rooney, dear Miss Salam, do you have my voice? Oh, okay, okay. Yes. Dear Mr. Samir, still, if you have still my voice, please. Okay, perfect. Thank you very much. Yes, please in the Q&A, give me feedback. Very low, but you can hear. Okay. So it shows that, for example, the testing program can be very comprehensive, or even without any testing in some situation, for some kind of analysis, there is possibility that we use this, and the knowledge factor is the penalty that we get. Instead of 1, we get 0.9. So Mr. Askur feedback me that the sound is very low. Please, other colleagues also feedback that if the situation is not good, I know. Okay. They also for the drawings, so sometimes the design drawings are available. Sometimes we should survey in the field. Sometimes the design drawings are available. Sometimes we should do the field survey. So you can see for each situation, at least 2 options are given. 2 options are given. One using the design drawing if they are available, and one doing the field survey if the design drawings are not available. And I repeat that for the life safety damage control, you can also use these options too. So you are not limited to these 2 options. And then if you have the design drawings, the condition assessment is less, just visually, because you have the drawings, but you will check the drawings. But if you don't have the drawings and you should do the field, you should find the field drawings, you should survey, so is more comprehensive, the condition assessment. All the requirements of these test, drawing, condition assessment for each material, for example, for concrete in their respective chapters. Then, based on the beam, what is the section area, what is the length of the beam, is the concrete material in this beam is good or bad. Also, the reinforcement and concrete strength. They are, after doing this part, which is the most difficult, most time-consuming part, will be resolved. Therefore, for you, dear structural engineers, that doing the design of new buildings, our most important responsibility is whenever we design a building, we make sure that all the documents, especially the drawings, are correct and in good situation. Because if we have the drawings, then later when these buildings go through the retrofitting, we don't need lots of field investigation, which is very costly, very time consuming. So please, if during construction some revision is being done to the work, please make sure that all the revision be reflected in the drawings. So if we, as engineers, we make sure that our drawings are good enough and shows the reality of the building, that's a very important contribution of us for the safety of our buildings. Thank you very much for our dear colleagues that feedbacking me regarding the voice. Please do that. Then, after this second part, as I mentioned, one of the most important part of this is the test, because testing, especially material testing, is buildings. Many of the property managers, they don't let you to do the test because it's just damage their property. So usually the existing building codes, because of that, is sometimes they let you to use the information in the existing drawings or documents. And in many of the existing building codes, they are also some values as a default, that whenever you can use that option of not doing the test, you can use those values. But the only point is, in systematic evaluation buildings, we need two numbers for the strength of the material, F prime C, Fy. We need two numbers. One is the expected value, one is the lower bound. Because when we want to use the material properties to calculate the strength of the force control elements, we are a little conservative, so we use lower bound. When we want to make the calculation of strength of the deformation control forces, because it's less scary, we use the expected value, mean value. Lower bound is mean minus one standard deviation. Therefore, because sometimes the codes let us to use the values in existing drawing, existing documents, so they should give us a factor that we use those numbers as lower bound and increase them by this number to make the expected values. So, for example, if for concrete compressive strength, they let us to use the value in the documents as a lower bound and multiply by 1.5 becomes the expected value. The other thing that is handy is the default values. In many countries, they have gathered the historical data. For example, they know in each different period of time period, for example, beams, in slabs, in footings, what was the lower bound compressive strength? What compressive strength was common at that time? With the material that they had, with the workmanship that they had, how much strength they could reach to at that periods. So, for example, this period between 7 to 17 megapascal for footing, this period 21 to 28. So, according to the previous table, if you are allowed to use the default values, this kind of information for each country is very useful. You can see this for the concrete, and here in this table we have it for the reinforcement. So this kind of tables is another options. So either we use the default value, or we use the values that mentioned in the documents and in the drawings, or we do the testing in the site. And usually the existing building code give us a couple options at least. But if we use the more reliable one, the value of the knowledge factor will be 1. But if we use a less reliable approach, the value of the knowledge factor will be less than this. So, finding the condition, finding the configuration, finding the dimensions of elements are very important. Material is very important. Also, the condition, configuration, dimension of elements are very important too, because otherwise we are not sure that the model, computer model that we have is correct. Therefore, it's important that we check the dimensions of the beams, columns, the condition and the dimensions of the elements. The condition, usually check the condition of the concrete, is it good or not, and using non-destructive testing, find out the location of the reinforcement, and especially if we have some drawings, we can cross-check with this checking in the site, with non-destructive checking in the site. And if we don't, some of these points that the non-destructive is being done, then we uncover the element and see the if the accuracy of the work is good enough or not. And usually in the site, the importance of the operator, experienced operator, his experience or her experience, it is much more important than the equipment that they are using. Sometimes you see that the experienced operator with the old equipments do very good estimation, but sometimes a less experienced operator with very nice up-to-date equipments give you wrong information. So the checking of them by uncovering some places is very important. Usually when we want to model, we want to check, it's important that we remember how they calculate, how they found out the properties in the site. For example, in some elements like diaphragms, like slabs, one side the information is more accurate than the other side. For the foundations, many times you see that when you uncover the foundation, the situation is quite different with what we have in the drawings. In buildings such as reinforced concrete, the use of non-destructive testing is very popular, very important. Most of the codes for existing buildings don't let us to use the strength that we get from a non-destructive test as a measure of strength. They just let us mainly, most of the building codes for the existing buildings, let us to use the non-destructive tests such as Schmidt-Hammer to check the consistency, to check the uniformity of the concrete. So based on the results of the Schmidt-Hammer, for example, we find out the concrete of this beam and concrete of this column are the same category. So when we want to design the location of tests, or when we select from this type of material a few tests, destructive tests, and then based on the non-destructive test, we found out that some other elements, they are again the same. So we also select some tests from those location. And then when the results come, results of core or couple comes, then we use those numbers that we derive from specific points to those locations that they, based on the non-destructive test, they are uniform, consistent with this part. So non-destructive testing usually is not allowed in most of the building code, is not allowed to use as a measure of is a measure of uniformity, a measure of consistency of the material. For strength, concrete, core and couple, destructive and semi-destructive tests are widely used for estimation of the, as I mentioned, concrete strength, as you know. And as you can see, really messy operation. So it is very important that if we do destructive tests, if we damage the building, if we make much disturbance for the occupants, at least the results be useful. Therefore, if, for example, equipment is vibrating, if the cutter, the blade is not sharp enough, so the sample gets lots of small cracks. It's not visible, but get lots of cracks. And when we test this, we get the lower values for the concrete, and we use these lower values in our structural and building model, and the building becomes vulnerable, which is maybe is not, because the way that we derived the material properties really was not good, and the value of the strength is reality is much more than what we get after this many effort, after this many permission getting arrangement, and then the result is misleading instead of helping us to give a good estimation of the condition of the building is just misleading. So it's very important that the procedures of testings be done. We do enough ferro scanning and locating the location of the reinforcement carefully, that not to damage the material. But anyhow, sometimes it will damage, and so we both for the holes and the damaged reinforcement, we should repair them. Anyhow, the most important, time-consuming, and costly operation in the systematic evaluation is the field work related to the estimation of the condition of elements and material testing. So we should be very careful that do these procedures carefully and get good results. Otherwise, it's just waste of time and money. Therefore, usually we very quickly pass the data collections, but in the reality, data collection is the most difficult one, the most time-consuming one. Part of a systematic evaluation is this data collection. What is the configuration of the building? What irregularities has? What are the dimensions of the buildings? What are the dimensions of the elements? What is the condition of the elements? What is the soil properties? These are gathering this information is the most important thing, and is the most contribution that our dear engineers can do for the buildings. Because right now, we are supervising construction, we are designing buildings, So we should make sure that the end results, the drawings, reflect all the changes that will go to the construction. The drawings be really as built drawings. And when we did all these based on that table that I showed, we will find out the value of the knowledge factor. And the knowledge factor value will be applied only to the existing material properties, not to the new materials. So when we evaluate a building, if we add some elements to the building during the retrofitting stage, those are new material, and there are the original material in the elements in the building, those are existing material. So when we model the building, original building, plus the elements that are newly added, we should remember that kappa, the knowledge factor, will be applied based on if we use nonlinear procedures or linear procedures in the strength or deformation capacity of the existing material. For example, in linear procedures, we're dealing with the forces. Even in the deformation control linear method can give us the deformation, plastic deformation. So for the deformation control and force control, for the existing material is either expected or lower bound. Expected means mean value, lower bound means mean minus one standard deviation, Then for this existing action capacity, for shear, for bending, for axial, for torsion, in that existing elements, for the deformation control, we use kappa multiplied by the expected capacity. And for the force control, kappa times lower bound capacity. But for the new material, we don't use the kappa. We don't reduce their value because they are new material. Our information maybe is not good for the existing elements, but should be good for the things that we add to the building. For the nonlinear procedures, the same. The kappa will be for the existing component. For deformation control, we apply to the deformation limit. For the strength, because for force control, we don't look at the deformation capacity. We don't rely on the plastic deformation. For force control, we rely on strength. So the kappa for the existing component times the lower bound capacity of what is times the deformation limit. But for existing, just for existing, for the new elements, we don't change the values. We don't modify the values for the new elements based on the knowledge factor. Therefore, we are looking at the structure of the chapter concrete. In scope, give us the when we can use the requirement in this chapter is not for the damaged building, it's for the existing buildings. In part 2 is the most important part. We quickly pass it, but in reality, in the project, it is the most important part. Then, in last part of the general requirements, because after these general requirements, we go to the systems and to the elements. In the last part of the general requirements, we are looking at the some requirements that can be used in most of the systems and most of the elements. So we bring them out of them and we talk about them once for reducing the number of repetition. For example, the table for the effective stiffness, because that concrete elements, even in their linear range, they get cracked and their stiffness changes. So we use effective stiffness. We don't assume that this part is non-linear. In reality, it's non-linear, but for the concrete elements, we call it non-linear behavior when the longitudinal reinforcement get yields past the yield limit, not the concrete before the reinforcement it gets cracked. Still, in the general behavior, we assume is in the linear range. Therefore, the effect of that cracking we include in the calculation by modifying the stiffness, as you know, and only the flexural stiffness will be modified. If we have here, for example, 0.4 in shear, it's not that it was 1 and because of cracking it becomes 0.4, because shear is not proportional to E. Shear is proportional to G, shear modulus. And shear modulus is almost 0.4 of E for the concrete. So here is G and is not changed for shear. Only for flexural rigidity, the E value changes. It depends on the situation, as we have in our ordinary new building design. Here for the evaluation the same. So one of the, as a sample, what in the general assumption and requirement are given, general information such as coefficient for cracking. The factors for cracking are given in this one. What else are given in this one? Give us some more samples. Another thing that is very important and given here is the effect of deficiencies, which is one of the most important things. In this general assumption and requirements, the sum of the deficiencies, how we should model them. In a new building, if the hook bars, lap splice bars, straight bars, if they don't meet the development requirements, they should be demolished. And we should make a good element with good straight bars, hook bars, and lap splice that do meet the code requirements. But for the existing buildings, all of them have problems. We should model them. We should bring them to modeling. And a few locations we consider, for example, this deficiency. When in our existing buildings, the straight bars, their lap splice is not enough. Their hook bars are not, for example, the shape that is needed. So what we should do, for example, says that you modify the yield reinforcement. If instead of this amount of the development length, you have a less development length, so with this ratio, not linearly. In the first version of this code, it was linear, but later with the more data, they modified this with this type of equations. So based on the what we have, what should we have, how much we are far from the optimum approach, we reduce the value of the yields. So in the general assumption and requirement of the material sections, teach us how to include this deficiency specific material is common, how you include them in the modeling. Therefore, for example, this effect, we will see later, we will see in the tables, for example, beams controlled by inadequate development of splicing along this. Then they have a, here you say, okay, it is instead of A, the ductility of this element, B, for example, point B, for example, 0.5%, 0.3%. And also, the value of the even be this much efficient as retrofitting or less retrofitting. So we are trying to use all the it or in your model don't consider as a load, lateral load bearing. But if it deficient, as much as it, yes, not forward by pointers in general assumption requires these cogs also. What else we have in this part to the deficiency? Still, we are in that 10.3 general assumption and requirement. In that part, I've selected a few of the topics in that part to give you what is general information are provided there. They try to give some means, some tools for us to differentiate between critical and less critical parameters. So, as I said, that we are in the comprehensive evaluation, we want our approach to become complex. We ourselves introducing new index, so we want to differentiate between two points. So because if we want to assume these two the same, we should use the lower value for both of them, and that becomes our estimate. We want to, as much as possible, differentiate, make it difficult, make the retrofitting cheaper, make the modeling and the analysis difficult for a structural engineer, deals with the systematic retrofitting, but make the cost of retrofitting, disturbance of the applying retrofitting as less as possible. So, for example, here, another coefficient is introduced. So, related to ductility demand is a demand, is not capacity. For example, in new codes, we have some provisions. We make a moment resistance that are more ductile, less ductile. We call it sometimes, for example, the highly ductile or intermediate ductility or low ductility. Those are capacity. When we apply those requirements in the building codes, our element becomes the ductility enhances, the capacity enhances. Here, no. Here we want just to see that there is some deficiency. There is some deficiency in this beam. Should we make a big penalty for this beam or make a small penalty? So we want to differentiate, trying to reduce the conservatism, our estimation. So this factor shows us this part of element is very dangerous, is very critical. But this part is not critical. And what is the measure of criticality? How much plastic deformation, how much damage that point has compared to other? Is it less than 2, between 2 to 4, more than 4? What? Damage, displacement, ductility, plastic deformation. Or if we do linear analysis, demand to capacity ratio. Demand to capacity ratio shows demand in this, the bending moment here is 200, but the capacity is 100. So demand to capacity ratio is 2. Damage to this point is 2. The other point, demand 300, capacity is 100. So this damage to capacity ratio is 3 times. So it gets more damage. So is less than 2, between 2 to 4. Low ductility demand, moderate ductility demand, high ductility demand. And what is the use of these things? The penalty will be different. And that's what we want to apply. We don't want to apply the same penalty. Because in places the transverse reinforcement doesn't have the minimum requirement, you should be all of them ineffective. All of them ineffective. But instead, now we can say, if it's this, 50% of that is effective. If it's this, all of them is ineffective. Because here is a location with lots of damages. But here is not that much damage. So we don't treat these two the same. And that's the general approach in systematic retrofitting, that we call primary element, secondary element, force control actions, deformation control actions, lower bound capacities, expected capacities, and so on. We want to differentiate, and if, for example, lattice splice transfer reinforcement shall be assumed if it's not according to that, it should be not more than 50% effective in region of moderate ductility. Have the minimum requirement, but we assume 50% of them in modeling. But ineffective in region of high ductility. If it's high ductility demand, then so a very important aspect of this systematic existing building codes is that deficiencies and different level of deficiencies in our modeling. It is make life difficult for a structural engineer, but for the owner, he will be happy or she will be happy because we save money, and because money is not in the modeling and calculation. The money is in the price and cost of retrofitting, the time that we disturb a hospital to apply the retrofitting. And this section, for example, sometimes we see that this section of the hospital that we should be closed, for example, for 1 year to apply the retrofitting. This is the only section that treats this kind of patient in the whole region. So it's not important that our work as a structural engineer increases in systematic retrofitting. It is important that the value of the retrofitting decreases. What else? So we have some general items at the beginning, like scope, like very important, material, very important, general assumptions. Then we have the systems. We have systems, and then we have elements. For systems and elements, our approach is the same. If we look at all of them and divide the situation. For example, look at this 10.4. If you look at this more carefully, concrete moment frames, these concrete moment frames, 10.4, now itself, it has subsections. So for concrete moment frames, as one of those systems, one of those many systems, the material is very systematically distributed in these sections. There is one section that shows the types of concrete moment frames. For example, reinforced concrete beam column moment frames. Usually, we consider these as moment frames, beam and column. But sometimes there is no beam, it's just a slab column moment. And sometimes the beam is post-tension or pre-tension. So post-tension concrete beam column moment frames. These are these three: reinforced concrete beam column moment frame, post-tension concrete beam column moment frame, slab column moment frame. Each of the systems or each of later elements, if we look at them, for example, reinforced concrete beam column moment frame, always there are 5 categories of information in this systematic existing building codes. Always you can find 5, but one of them is very important. Others are not that important. So we have 5 information. First, the definition, some modeling aspects of those that specific systems comes in general. Then how to model stiffness. For example, for beam, should I assume shear stiffness, bending stiffness, torsion stiffness, or not? Just shear and bending is enough. Axial stiffness. Should I include the part of a slab as a beam in calculation of it? All comes here. How I calculate the strength of the beam columns if I'm doing the linear analysis and there is possibility of the weak story. How I check the strength of the story. All these comes in this. Important. But the most important part in every system, the heart of systematic evaluation is for each system or element is in part 4. Acceptance criteria for that system, for reinforced concrete beam column moment. Acceptance criteria, which are those tables and the information and discussion that give us both modeling parameters and the acceptance. So that's the most important thing. This is nothing, because really a code shouldn't give us the retrofitting measures that how you should retrofit this system. The same as new building code. Never in a BMBC says that if you have a 4-story building, you should have make it a steel brace system. No, if you want to a steel brace, gives you the R factor and the procedure for the design. If you do reinforced concrete, if you want to masonry, so the procedure given, but it doesn't give you the system. In the retrofitting, the same. But again, there are lots of experience that, for example, for reinforced concrete beam columns with this with deficiency in the connections, in deficiency in beams, deficiency in columns, deficiency to the lap splice. What is better? So there are some information. But the text of code, they don't put those information, but they need this. So in commentary, they can say is not as the code. So in the code, always see here a paragraph, something like that, very easily. But then in the commentary, it gives you that usually the reinforced concrete beam column elements frames with this kind of deficiency, usually this kind of retrofitting technique is good for that, and those information comes there. The information are very nicely, very systematically, very with a structure is divided for each system. And as I mentioned, the most important is the title of today's presentation is the acceptance criteria and the modeling parameters, which, for example, here when you go, you have seen that many times, this table. That gives you everything that is needed for the modeling and acceptance. So powerful tool that now, as I mentioned, many structural engineers say that we don't need any new design, we don't need design code anymore. We go and build whatever we want. We go and build whatever we can. So if there are some deficiency, we model it. And then we show that it doesn't pass the those performance level. But there are a strong resistance to that because they say there are many of the experience of their generation of the code writers. They believe that we can miss many things in modeling, in calculation of the level of loads, in calculation of the behavior. There are some unreliabilities that is better that we use the experience. We use the prescriptive, keep the prescriptive articles in the code, keep the empirical approaches, try to use them as much as possible, but complement them with those. So still, most probably we will have our descriptive load articles in the course at least for a while. So this is the most important for each element. Steel, concrete, for each system. For example, reinforced concrete beams, columns, in each system, for the linear and non-linear, we have these tables that the modeling parameters is there. And all these tables are for force, not for force deformation, for deformation control element. The ones that get damage, A, B, and C, is for the, if it's linear, it's force control. We don't need these things, we don't need these things. For force control, we just need to calculate the lower bound strength at B and be sure that the demand is less than the lower bound capacity. That's it. In linear analysis, in non-linear analysis, the same. But for the force control analysis, in linear analysis, we look at that how much is passive, how much is the DCR, demand to capacity ratio, and then there is M factor. If it's 2 times, is IO. If it's 3 times, is LS. If it's less than 5 times, is still you didn't pass the CP. But and for nonlinear analysis, it gives you the value of the plastic deformation. So this A and C, which is the capacity curve of that force deformation. Tables are just for deformation control procedures. They are very good for all the different situation, all different, usually there are few pages, all different deficiencies that they may have, the values are given. So all the deformation control parameters can be modeled with inclusion of all the inadequacy that they have, deficiency that they have. If there is inadequate embedment in beam column joint, if it's inadequate development of splicing along the span, and these are controlled by, this part is controlled by flexure, controlled by shear. So all combination of situation that may happen, we have for existing element, for the deformation control parameters, we have their modeling. And then on this modeling parameter, which is the capacity curve of this element, force control, deformation control action, then we have the limits for the performance. That how much damage, this much damage is IO. This much damage for primary element is LS. This much damage for primary element is CP. For secondary element, we accept more damages. But for primary element, we usually look at the primary element, IO, LS, CP. They are all the plastic rotation acceptance criteria are given. So really, these tables are a new word for us as structural engineers. In a way, is modeling and analysis versus prescriptive experience, empirical approaches. And then by having these values, then different softwares are ready to apply these modeling parameters to their deformation control actions, and then calculate the target displacement that is dependent on the level of earthquake in the formula, then push the whole building that consists of these deformation control parameters and see what happens. When it reaches to the target displacement, each deformation control element are at what stage of damage, which is correspond to which performance level. It is between, for example, life safety to collapse prevention. And when it comes to here, at the same time, no force deformation parameter should passes the lower bound. Here is expected value. When we calculated the strength of this deformation control, in the formula, for example, for bending strength of the beam, we use the material expected values characteristic. But for the force control is lower. Then applying in the software becomes very easy. Usually the softwares ask us, what are your deformation control? We say is a frame, so in beams and in the columns can get damaged. No, is a bracing system. So in the axial force in the braces, it can damage the fuse. The deformation control is the braces. Now is the eccentric brace system. So the shear in the link beam is the deformation control parameter. So we select the kind of points that our software should look at the damage at that point. So we select the templates that this is a moment resisting frames. So in the beams, at the end of the beams is a location that it can get damaged. Look at the deformation capacity, and we give you the property of that spring, that nonlinear behavior at the end of the beam, which is that modeling properties. So if this template is applied to a beam, this general shape that in the vertical axis is the force, in the horizontal axis is the deformation, and this force is divided by a scale factor, deformation divided by a scale factor, and then this is general shape. If it's not according to our code, according to the table of our existing building code that we are following, we change the numbers here. We change the number here to become similar to the code. Then we apply this, we ask the software that at this point in this beam, with this property, this reinforcement, this dimension, I want this situation. And then for that specific beam, for example, element number 100, at the beginning H1, at the end H2, it shows us that for that specific element, these scale factors, which are the, for the moment, is the moment capacity of that beam. We will have it here. We can check that if the software calculated the strength of the moment strength of the beam correctly, in positive or negative, based on this reinforcement, based on its dimension, or not. So then modeling, either we trust the software or we check and change the properties to be sure that it applies according to our tables. Then we say that we want this building to be pushed to this target displacement with this lateral load distribution with this many steps. If it was get some problem in convergence, we increase the number of steps, so the numerical stability can be guaranteed. And as we saw, software tries to reach the building to that target displacement that you assign. And in each step, in each step, it give us that what is the situation of the all the deformation control parameters. How many of them are in the linear range? How many of them pass little and linear range, they pass the point B, but still they are not in the IO range? How many are in this range? At each stage, each displacement, each target displacement is more, but each displacement we can calculate what is the SAA that makes this much displacement, and we can say this is corresponding to a 100-year return period earthquake. This is 200. This is 300. This is 400. And see, as the level of earthquake increases, how the damage distributed among the deformation control parameters in the buildings. How many at each stage for the, for example, 300 return period earthquake, which is corresponding to this much target displacement, 8 of the force deformation control parameter is between LS and CP, but none of them pass the CP. Is here, life safety and CP. Our dear colleagues, if you can give me a feedback in the Q&A that the voice is hearable, is acceptable or not. So, a little worry that with you or not. Voice is very low. Oh, okay. Thank you. So, therefore, these softwares provide a very good visual view of our design, that the distribution of damages along the different bays, different stories can be seen very easily over here. Now, if we want to apply this in real life buildings, if one as a structural engineer wants to perform systematic evaluation on a building, because we used to, even in design of new buildings, that there are different approaches that we can use. But the principles for the existing buildings a little bit are different with the new buildings. To make my point, I try to find a simplest possible example. What I mean that we have different methods for analysis: linear static, linear dynamic, non-linear static, non-linear dynamic. So at least we have 4 types of analysis. Usually in the new buildings, when we design, we shouldn't expect that much difference between these, because we scale. If we use one approach to the or other approach, there are some scaling sub changes, so they are not much different. But in the evaluation of existing building, that's very critical. So I want to reach to this point that for systematic, there are lots of ways to evaluate a building, but for the systematic evaluation, our view for selecting a company, selecting a person to do the seismic evaluation should be quite different with the way that we select a company, select a person to do a design for a new buildings. Usually in the design of new buildings, we select a person, company that ask for less money and give us because the procedure that should be followed is almost straightforward. The steps that he should or she should follow is straightforward and easier. But for the existing building is quite different. Let's look at this example. The easiest reinforced concrete moment frame that we can select, for example, is a internal frame in a very simple building like this. We check a 4-story, 6-story, 8-story, and 10-story frame with all the 4 methods. And to make life easier, just look at the result. Many times results like this that we solve from this example. Beams and columns, number of elements in need of retrofit. We use a method. This method says 50% of the beams need retrofit. Half of the beam. We change the method. It says 25%. We change the method. It's 0. 0. 50%, 0. So the first thing is lesson that we learn that in the seismic retrofitting for a specific building, because if you apply the seismic retrofitting for a group of the buildings, you should make a methodology and use that for all the buildings. But for one specific buildings, you should try all the available analysis methods. Because one of them tell you that 70% of the beams need retrofitting, one says 0. Now, if I select a person that gives wants or a company that wants less money to do the calculations, they will go with a simpler way, a simpler approach that they know. So I pay less, I'm happy, but 70% of the beams should be retrofitted. Didn't need at all. In total, for example, 60% one method, 45% another one method, 0. Or the same you can see here in the columns. So the change is really too much. Is it possible? Yes. This is the simplest. It's not a complex building. It's not an irregular building. It's the simplest possible thing that we can think of about. An internal, very regular frame. So no irregularity, no complexity. So this is the issue with the existing buildings. Our approach should be different for a specific building, especially for a little larger buildings. It is very important that the evaluator checks different methods for that. All analysis procedures. It takes time, it's difficult, but it's a desk work. It's not that you go to the field and retrofit 70% of the beams, almost all the beams. In the retrofit, in the evaluation and retrofitting, the cost is in the applying retrofit. The cost is not in the evaluation phase. So we should learn that the institutes, the authorities should learn that here you should expect good work, but pay more. Because at the end, this calculation and modeling is not costly. The applying retrofitting is costly. That you come and 70% of all beams, all columns, you retrofit them. For example, use FRP for all of them, but you didn't need to do that if you use another method. Let's, from this simplest possible example, go to the largest ever. This is the case of seismic evaluation and retrofitting of a 56-story building complex in Tehran, Iran. At the time that it was under seismic evaluation, it was the largest evaluation project in history and in the world. I don't know if after that this status changes or not. It's around more than 15 years ago. But at the time, it was the largest retrofitting project in the world. A 56-story building with a long story, that why it went through the retrofit. So here the same story, again the same story. If we look at the results of the linear analysis, these are this kind of buildings, like a star. They are very nice buildings. They are very nice buildings because the shade is like a star. The ratio of the parameter with the area is more than other shapes. So the apartments we can have lots of view in the parameter. But from the structural point of view, because the main walls are intersect here, they have a little problem with torsion, that these lateral walls of apartments should get that torsion. Anyhow, if we go with the linear analysis, for example, in these cases, and sometimes linear, sometimes static, sometimes dynamic, it's not that always one of them gives us the less overestimation. It's different, but many times the nonlinear ones are better estimation. So with some form of calculations, almost 20 story of the first 20 story, most of these walls in this huge building should be retro. 20 story, almost all the walls should be retrofit. Here, assume everything is more than this, need retrofitting. For example, this wall in wing A, from the this floor to this floor, floor almost 20 something, 26, 7, need retrofitting. But I think that's maybe the first real building that used RAM Perform for a project. I think was this building. You know the Perform software now is CSI Perform. But when it came, when Professor Pavel of Berkeley was retired and worked with the RAM company to produce Perform, and the Perform software was used for the analysis, lots of problem, and needs some solving some of problems to be run. But anyhow, lots of problem, lots of difficulty. But what the importance is, then you just in some of the lintels, and they need just retrofit for this huge 56-story buildings. Instead of 20, 25 story, almost all the walls should be retrofit. Huge work. A couple of a few of the lintels in the main walls, they need to, their beams, those lintels, they need to be retrofitted, which is easily being done. So yes, there was need to derive the site-specific records to obtain software, solve the software is not running, the difficulty modeling problems, lots of work using the experts from all over the world, paying lots of money, but compared to performing that retrofitting was not. One of these apartments, the value of one of those apartments was more than all the project for the evaluation. Therefore, the lesson one is for us is that in a evaluation of the particular buildings, we better to perform different. If all those approaches that are permitted, because sometimes they said that, for example, for this building you can do the nonlinear static. You can do only nonlinear dynamic. But if you can do a few of those, better to do all of those. So if we look at what we had in these 4 sessions in this course, we covered only some concepts regarding systematic seismic evaluation of existing. This area is very vast, very large. It has seismic evaluation, it has seismic retrofitting, technique selection and detailing. We didn't say anything about technique selection and detailing. Even in seismic evaluation, there are methods based on fragility, vulnerability function, visual skimming, rapid vulnerability, preliminary. We talk about some concept about detailed engineering and systematic evaluation. But there are much more here. So we should know that we focus on some concept because mainly for us, it was important to differentiate between our approaches to the new building and to the existing building. But there are lots of good references, lots of good books. For example, I use mainly this code as a base. There are many other codes can be used, even for the in ASC 41. Now every chapter for materials, now they are getting separate code by the relative, by its corresponding code committees. For example, CHAP ECI has the assessment, repair, and rehabilitation of existing concrete structures. AISC has the assessment, repair, and rehabilitation of the steel structures. So now it becomes even more technical. And for the examples that some of our dear colleagues were asking for the examples, there are again many good. I selected this one because it's free to download and easy to download. The examples guide for AC 41, previous version of this, but with additional commentary for AC 41-17, and the based on 17 is it seems is coming out soon. So there are very good codes, many good from different countries. I didn't put from New Zealand, Japan, from Australia, from the Eurocode. Also for the seismic retrofitting technique selection and detailing, the part that many of our dear colleagues like this ones. When it comes to the seismic retrofitting, everybody likes what techniques, what details, how to design this special technique. You as engineers, we love mainly these things. But the contribution of the systematic retrofitting is that modeling and the acceptance criteria. It's not the technique. Techniques, there is more straightforward how to approach. For example, this reference is very good. Techniques for the seismic rehabilitation of existing buildings from FEMA. Again, I selected this one because it's free upload, downloadable. Very systematic approach. How to select Japanese from long ago, also other people involved in the retrofitting. They have very good systematic approaches that you can find out in many references. For example, here, the approach in general for a building, for a vulnerable building, the approach is that you divide all the deficiencies to 7 groups. Here, this table, I brought only 3. The other 4 are here. This is all the deficiency in the buildings are all their global strength is less, or their global stiffness is not enough, or their configuration has a problem, or the detailing of the components are not good, or the load path is not good, or the diaphragms are not good, or the foundation is not good. So 7 deficiencies. Each building can have 7 deficiencies. And in general, we have 5 approaches, 5 solutions. Either add new elements, enhance existing elements, improve connections between elements, reduce demand, or remove selected components. So, very systematic. For every case, so for example, in this book, for every system, it mentioned that, for example, for steel bracing systems, these 7 deficiency and 5 solutions explain that these numbers is referring to different sections that if is the global strength of system is deficient, how to deal with that, which solutions is good for that. If you don't want to do that, if you want to reduce demand by damper, by base isolation, by whatever system that reduces the input to the system, what are the good options for this specific, for example, reinforced concrete moment resistant frames. So when it comes to seismic retrofitting technique selection and detailing, there are very good guides available as a catalog that we go through when we find out what is our problem, what is the problem of the building, and try to solve the problem. Sorry, okay. So, because as I mentioned, there is compared to the new design, the evaluation and retrofitting of existing buildings is more complex because it's not that straightforward. There are many ways. For example, if I can change this to now our building is this, it mentioned here, unrestrained here. So, for example, the target displacement is this point, but the building arms and goes down. The base shear top displacement can't reach the target displacement. Now we have to reach to the accepted performance level. There are many ways. If we can, in any way that we can come to this area, it is accepted. So you can increase the stiffness, and the strength. Then, because of that, your target displacement after yielding reduces. So, with increasing strength and stiffness, you can reach to the safety. Or you can increase somehow strength but not as much as this. But not rely more on ductility and reach to the safety. Or don't increase at all the stiffness. Don't increase at all the strength. Just increase the ductility and reach to the. Therefore, there are lots of ways. And the second important lessons, the first important lessons for us was we should apply in one building that we want to focus, apply all available method of analysis. Second is check many options for retrofitting. So those, if a company you ask for less, then we do less. You should, if you are in charge of an authority, for retrofitting, it's better to pay more to them, but ask them to do more too. Not to pay more, but they do less. Not to ask for just pay, but don't control. Therefore, if we so, for example, in that case, say assume that is a hospital. For a hospital, we can either here there is a problem. This existing structure can't reach to the target displacement. So either we increase the strength and stiffness by adding these new elements, and then reducing the target displacement. Now, even that vulnerable element here doesn't need to reach to this level of displacement. And at this level of displacement, it is okay. Or just that vulnerable element. We don't increase the strength. We don't increase the stiffness of that. Just see what happens to that. Why has a reduced ductility? So, for example, now because for example, we need to increase it by adding some cover of concrete or steel coverage or FRP coverage just to enhance the stress strain curve of the concrete and increases the ductility capacity of the section, and it reaches to the target displacement. So making smart decisions is very important. So our second lesson is we should use different approaches and then do the cost benefit, because sometimes for us is retrofitting from outside is better not to going inside. Sometimes we want to go inside if it causes less cost for the retrofitting. So depend on the situation, we have different options available. Then for the systems, selection of systems, many of these approaches based on experience, as I mentioned in the quotes in the commentary part, give some recommendation. For example, many times retrofitting from outside is easier. For example, in these cases, you can see that a bracing system is added, in fact, to the perimeter of these buildings. In some of the faces, it is less, some complete, or just some support from outside. We know that some systems, such as BRB, these buckling restraint braces, they are very good and easy in a way, because bracing system is very good. The system, no problem with bracing. Just the point is in the tension, it is very good. But in compression, then buckles. So if it just, we didn't have this buckling, if it was buckling restraint, if it was BRV, it was very good. So just put element, and this element cover just keep the brace from buckle. So the brace that wants to buckle comes and touches this cover, and it doesn't let it cover, and it doesn't need to be very strong. Just a small force can change the buckling mode of this brace, and then the behavior, even the compression, becomes almost similar to the tension. So very good, promising approach. It has some problems. They are working on that, different techniques. Different countries are working very good. For the masonry buildings, usually one approach is to design rigid cores along the plan of the building. So a distribution of these rigid cores is very good. And for the local problems in the elements, usually techniques such as using FRP now is very good, but should be used very carefully, because in many cases, due to workmanship, due to material that it used, there are projects, for example, a very important hospital, you can see that they spend lots of money on the applying the FRP, but around 1 year after the application, you go and check the locations. Many places the FRP is separated from the concrete. So the detailing is very important. The detailing. When you select the general system, then the detailing is as important as the system itself. And the detailing in all the system, complex and simple retrofitting are important. Because, for example, you want to retrofit from outside, either by adding bracing in outside, or adding the shear walls, or adding frames to outside of the buildings. Then many times, because only at the outside is retrofitted, the diaphragm should bring the force to these elements in the outside. So it's better to be rigid diaphragm, because if it's flexible diaphragm, the internal elements that are not retrofitted, they will get also depending on the mass distribution of the diaphragm, they get lots of load too. So it's better to be rigid, and then so detailing are important for us to really building after retrofitting behave the way that we are assuming. We assume that the load comes to these elements in the perimeter. So there is needed enough good detailing to make the diaphragm rigid, and the diaphragm can safely transfer all the loads to these elements in the perimeter. Also, if, for example, we assume there is a shear wall, and this shear wall in our model in the software, where we put the shear wall, and it works very good. Or in the software, in the reinforced concrete building, for example, we put the bracing, and we check, software says yes, everything is okay. But in reality, after earthquake, a couple cycle, this connection between brace and the element get loose, or the element, the brace is not completely straight when it's applied. Therefore, building should get deformation, then this brace come to the help and help resist the load. And because it's a stiff building, first the building damages, then you will added element wants to participate. Or, for example, if the connection between new shear wall and the diaphragm is not good enough, then the load from diaphragm can transfer to the shear wall. We assume that we design the shear wall to get a good share of the force, but in reality, because of bad detailing, the load can transfer. For example, damage happens in the slab because of small thickness that the slab has. Therefore, the detailings are very important, and after selection of the approach that we want to use shear walls, we want to use bracing, then designing those details that this retrofitting technique behaves with the original building in a way that you assume in your modeling is very important matter. Therefore, if we want to review the items in today's talk, because a test is coming up after the course, if we, one of the important things was this systematic assessment and retrofitting, what was the main contribution? Is it, for example, introducing new retrofitting techniques, advanced techniques, FRP, shape memory alloys, base isolation, new form of dampings, repairable systems, many new ideas? No. The most important aspects of the systematic assessment and retrofitting is introducing modeling parameter and acceptance criteria that we can model each building with whatever deficiencies that they have and check their performance. So this modeling parameters and acceptance criteria, this is the very important contribution of this generation of the systematic new existing buildings. What part of the systematic evaluation is more difficult, more time consuming, is the finding the building configuration and testing, finding the material properties, characteristics. So if we, from now, we can, at least for our new buildings, we can make a good documentation of the authorities can make sure that all detailed drawings are as built. It will be a big help later for the when we want to evaluate, we want to because the new code comes, the seismicity of the city changes, a couple new faults are discovered. So the most difficult time consuming is finding the building configuration and the material testing. It's very, very difficult to. I ask, many of you had this experience. Then, what is the approach in the systematic retrofitting and evaluation toward the deficient elements? Because in our design of new building, construction of new building, our approach is very clear. Very clear. You should demolish and rebuild. We don't accept any deficiency, any major deficiency in the building. It should be according to the what design. But our approach in the systematic evaluation, we model the deficiencies. So all the deficiencies are being modeled by modeling parameters, and their effects are being considered in acceptance criteria. The acceptance criteria of the, for example, this inadequate development case is different with the one with adequate development. Is maybe is 1/10 of that or 1/5 of that. So it's quite different. The effect of deficiency are shown in modeling and in acceptance criteria. There are modeling parameters in the tables, such as the one that we can see above. Why they are only for deformation control actions? Why they are for deformation control actions? Because force control action doesn't need tables. They shouldn't get damaged. So there is no need to the level of damage as a acceptance criteria to modeling the nonlinear behavior. So there is no table for the force control. Force control action should remain linear. Then what are if the major contribution is modeling parameter and acceptance criteria, what is modeling parameter in a simple talk? What is modeling parameter? This A, B, C. What we can call them? This shows the modeling parameter, shows the nonlinear capacity of a deformation control action. For example, here is bending. So nonlinear capacity of bending is a modeling parameter. A, B, C shows this capacity. This is capacity. Demand can be small. Demand can be more. Demand can be more. Demand can be more. Demand can be more. Demand can be different. What is capacity? The capacity to damage without deterioration. The capacity of damage with deterioration. So these are capacities. What is acceptance criteria there? If it's the capacity. On this, the limit for performance, limit of damage for performance, limit of performance on the deformation control action, these are acceptance criteria. So on this limit till here, this much damage is IO. This much damage is IO. So limit of performance. How much damage is LS? How much damage is IO? How much damage is CP? So acceptance criteria. Then this, if they are larger or smaller, what engineering sense should we have? If the modeling parameters are larger, if modeling parameters are smaller, this A value, if it's larger or smaller, what feeling we should get toward this deformation control parameter? If A is more, like a ductile behavior is more. Is A is less, so we can see that if the problems with the confinement and shear and the ductility is such a way, this combination, that the ductility is less, A is less. More, it will be more. So modeling parameters give us a sense of the capacity, ductility capacity, ductile behavior of the element. More ductile. How about acceptance criteria? If they are larger or smaller, what sense we get there? For example, here this value, if it's more, this value more or less, what happens? So if it is more, life safety is here. If life safety is here, the limit is more, the probability of passing that is less. The probability of satisfying that is more. Because if the limit is more, so you need more demand to pass that limit. More chance of satisfying the performance limit, more chance of satisfying life safety if the acceptance criteria for life safety is more. Life safety here is more. Then, what is the main usage of non-destructive tests? As I mentioned, there are almost no code. Sometimes in some guidelines they let, but generally you can find code for systematic evaluation of the existing building that let the non-destructive test their estimation we use for a strength estimation of the material. They are used just for the consistency, for uniformity of the material. That material all over the buildings are almost more or less the same, or at least find out that which elements their material are the same, because for example, Schmidt-Hammer really measure the surface hardness. Of course, surface hardness of concrete has relation to the strength of the concrete, but is not a one-by-one relationship. So there is possibility that the value is overestimated or is underestimated. Therefore, the value is not important for us. We want to check that where the values are similar. We say that the concrete of this location is probably cast at the same time. So these are almost the same material. If we want to arrange for the testing of the material, we select a few from this portion of the building. And if the results came, we want to extend these results in our model, those elements that with Schmidt-Hammer behavior are similar, we assign the value of the concrete strength. Then the knowledge factor is being used to modify component capacities. As we mentioned, we use the concept of knowledge factor to make some flexibility to the number of the tests and the level of the gathering for information that is needed, so we can have different options with different consequences. If we use this package, the knowledge factor is 1. With this package, the knowledge factor is 0.75. This package, knowledge factor is 0.9. So, but where it's applicable, just on existing component, not on new component, just on the existing component, the properties of existing component. Well, depending on nonlinear procedure we are using or linear procedure we are using, in any case on existing properties. For example, the strength of the force control material in nonlinear analysis, or deformation limit of the deformation control element in the for the deformation control element in nonlinear procedures. So if we look at the some of the outcome, in general, that the level of deficiency somehow is included in the modeling. We saw that both, for example, can change the material properties. Well, for example, Fy for when the lap splice is not enough, also in the modeling and the acceptance criteria it changes, and in the tables for these are for each system these are provided, and then we understand with those simple example of the one frame, and then that larger building as a at the time the largest evaluation project in the world, that both of them shows us the same thing, that in systematic retrofitting, one focus should be that we try to use as many analytical approach as possible for that specific building that we want to check for retrofitting. One. And also, there was two other points. The other point is that in retrofitting, we try to use different retrofitting techniques. So that's the second. And the third one is trying to increase the complexity of the model. For example, by modeling soil, by modeling the connections. You know that, for example, in the many codes for new building, we have the articles or appendix on soil structure interaction. And usually in the older approaches, we change the period of the building because soil is flexible, and increase the damping of the structure because soil absorbs some of the energy, vibration energy from system. So both of them usually causes lower the base shear. So generally, not always. Sometimes when we include the soil structure interaction, the deformation of the building increases. But usually the forces decreases. So usually the design base shear, when we use the those articles in code for the soil structure interaction, usually the base shear decreases, design base shear decreases. It becomes more economical to design buildings, including base soil structure interaction. So most of the codes for the new building code, they don't accept reduction in base shear more than 15%. 15%. But for the retrofitting, they accept twice that, 30%. And that's a large amount. So, for example, sometimes you design a building, it is vulnerable, but when you also model the soil as a springs, the way that is in the almost all of these codes for existing buildings, there is a chapter on the modeling of soil. It takes time for us, for an engineer to do that. It's difficult, but that's the sense. That's the approach. For the systematic, we want to make it complex. Because then, again, this 30% reduction, for example, in base shear, it can solve many things. Even 10% can solve. Now, if the 30% reduces, maybe there is no need to retrofitting at all. So, yes, we should pay the design team more, but the main cost eliminated. The main cost was the retrofitting. Finding another place, these buildings, they go there for a while. If it's a university, they go there, the labs should move, and then you retrofit it and then return. So all those costs are gone. So I think now good time to use the question and answers from our dear and patient colleagues. Thank you very much. So if I should try. Okay, thank you very much. Sorry, there are some of the remarks during presentation because of the voice. Sorry for that. Then one of our dear colleagues asked to identify inside old concrete strength test, the Schmidt-Hammer and wave velocity test has been used. Yes, that's true. The reliability of these two tests is how much with respect to core sample test. As mentioned, for the systematic evaluation doesn't let the non-destructive test to be used for the estimation of the strength. So only the core test or the couple test, destructive or sometimes semi-destructive tests are accepted. So here, in your case, just the core test is accepted. Oh, sorry again for voice. Yes, Miss Salam. Okay. Also help mention that you can increase, because I already did the approach that she mentioned. So she also shows some fixing approach for you to hear better. Then there is, how do we fix the ductility of concrete and rebar of an existing buildings? If the only problem is ductility, as that example that I said, for example, we see that there is a column that it reaches when we push this building to reaches to target displacement. This column, for example, or series of columns, they passes their ductility limit. So we should increase their ductility without increasing their strength. A column strength is mainly due to the longitudinal reinforcement. But if we just put the cover, steel cover, concrete cover, FRP, a jacketing around the element, just to increase to improve their forgot. Anyhow, if we could increase with this covering part, then the strength relationship improves. So in a way, but with confinement, I was searching for confinement. Just by increasing the confinement, you changes the properties of concrete. Before, it was a concrete with low strength and the low ductility and the low crushing limit for the strain. With some confinement, those increased. The material changed. Therefore, you didn't change the strength of the column or beam, because it's mainly due to the longitudinal rebars. You didn't change the rebars. You changed the properties of the concrete, and that caused the confinement. This much in average as designed for slabs and beams of a 10-story industrial building. It's mentioned that the members have casted by 50% of rounded. Okay, that's why. Okay, is good for taking vibration of machine. Is there any possibility of swelling for the rounded gravels? Of course, for the new buildings, there are a specific condition for using the foundation or the support for the vibrating machines, both for the concrete and for the detailing. But in general, as you mentioned, because of vibration, it becomes a little loose. But in our talk, if we want to include that in the modeling, we need to have a relationship between level of vibration and the loose of the strength, such as because regarding the damage, we have one approach in seismic design for the using ductility. Then we have the another approach. This is for low cycle fatigue for the elements that get damaged with a higher magnitude of the displacement, but not many cycles. But the other way, there are sometimes damage in the elements due to high cycle fatigue because the number of loading is too many times. So a train goes over the bridge. So many times this happens, and this vibration reduces the strength of the elements. So for in your case is mainly we need kind of this to use the level of vibration, the level of the reduction that we should right. I don't have any of if such things exist or not or should. So I apologize from our dear colleague, Mr. Kabir. Then weak and reduced lateral force. Is this force is considered for evaluation of existing building as the new in the load combination we had that, but as you mentioned, for even for the design of the new building, take considered as a governed seismic detailing because when you compare the with the wind-induced load in this element with the earthquake-induced load in the element, the earthquake-induced load is divided by R. But the load for is so therefore is the correct value, not divided by R. Therefore, the detailing is needed because that level then it is governed, but doesn't have that ductility. Therefore, of that they included that for the existing building to increase the strength for the existing building. So it is. Thank you very much, dear gentlemen. Can we use systematic procedure mentioned in ASC 41 in our country if site-specific earthquake hazard level is not possible to obtain? What earthquake hazard level we can select for performance evaluation when we wish to use ASC 41, and what performance level is appropriate for evaluation of seismic non-compliance building belonging to seismic zone 4. So, first of all, for the modeling earthquake, there are many approaches in many countries. In fact, they didn't have, all they had, at least for a while, was a size, the response spectrum for 475 years, which in the code, and or doing the site-specific response spectrum. So in many of projects that they wanted, for example, if there was a program for retrofitting of schools, so they had to do the site-specific response spectrum, derive the site-specific response spectrum for areas. So that solution is there. But for DACA, there have been studies, and there are new studies under this project, Raju, part of the URP, that provides the response spectrum for different return periods. That, for example, is a very good approach. Also, those coefficients that multiplies a level of earthquake by those coefficients to estimate another level, which, for example, 1.5 was very common to check from the 475 to 2475 year return period, from the 10% to 50 years to 2% to 50 years. But in general, we need that, and there are different approaches to get it. For the non-compliant building, exactly is systematic building, systematic evaluation is good exactly for them, because they don't have all the requirements of the building codes. So and the tool that we have in the systematic evaluation is that we don't want the system to have an estimation of R value. We just to have the properties of elements. This beam, this column, this brace, what is the situation, and then we have the modeling parameters, and then we have the acceptance criteria later to check. So we have exactly the tools for these cases. If it's if all the situation, all the requirements of the code are covered, then we can go with the R approach too. But this is exactly for the case that you mentioned. Please mention the retrofitting for of a slab column. And yes, in those, if you look at that retrofitting technique from FEMA that I mentioned, also there are lots more too. They have the requirements both for modeling, the code for the existing buildings have, and it's easy to in modeling, because a part of a slab is being modeled as a equivalent beam in the model. So modeling is not a big deal. But for retrofitting, and many times for the flat slab, they have the punching shear problems. And for the punching shear, there are different approaches to increase the strength. Very, very easy approaches. Many of them involves using the plates around to increase the punching shear capacity of the slab. But if you look at those references regarding the techniques, because we have says 3 levels, at least we need 3 levels of information. One level is how to model and to check the acceptance criteria, that what is the situation of your building, And then after retrofitting, what is the situation of your? Then we need some guidelines, some approach to how to select the retrofitting technique. That it is better to use the base isolation or adding the beam or adding the or reducing some elements, for example, removing the infills, the connection between infills and the frame. Building becomes less stiff and the flexibility increases, but the demand reduces. So we need some information about that, which again, those report that I mentioned from FEMA is one of them. There are lots of reports like that guide us how to select the technique. But it was one of the good ones that gives you, for example, 7 deficiency that buildings have and 5 solution, and for each case systematically says that for this case these 5, from these 5 these 2 are the most important. If you have this from this 7 you have this 5th problem, for example. So very system. And then the last one is to design that retrofitting scheme and the detailing for that. I assume your question is mainly this third one, that we know that what is the problem and we selected our retrofitting technique. Now we want to solve the local damages in the elements. So these details can help. Then how can we retrofit the steel buildings? For a steel building, many times their problems is with the slenderness and the buckling. Many times is because of that all their buildings. So depend on the situation, but because for columns many times to accessibility to the exact situation of the columns and the belts are not, sometimes is not good enough. Many times they try to use concrete, use those original columns and then encase them in the concrete and also use some elements to interconnect them and then put concrete, and that many times helps. But you should check the extra weight that causes for the heat and good approach. But for steel buildings, almost all approach one of good one removes the demand from the this flexible of the force. So reduction demand usually itself doesn't need any fit. You add steroids, the demand also reduces. So, and the other thing that sometimes for the steel structures like like brace puts too much demand. Their steel structures are not well detailed. This extra demand may cause problem. So it can separate the infill walls from the steel frame. That usually increases their performance. Just we should keep the top this from out of failure. And usually look at their steel structures. Mostly they are the systems have many moments.
Okay, so you and our dear colleagues hope to have a very nice night and week. Thank you very much.